this is Dr. Matt again. Okay, now that we understand Maxwell equations, it's time to use them to get to our final step towards the Bell's equation derivation called the Malus law. Yeah, Malus was this French guy, yeah, you know, once more. And this guy actually derived this law like in early 19th century, actually before Maxwell's law. But who cares, right? Yeah, right. Okay. Now, in order to derive, Malus law, which will lead us to Bell's equation, well, first we need to prove that the magnitude of B is proportional to the magnitude of the electric field here. So for that, we'll use Maxwell's third equation, which is this, if you remember. Well, first part is easy here, the partial derivative of the magnetic field over dt, well, is equal to the partial derivative of its coordinates. That's very difficult. Anyway, so that's the easy part. Now, the second part here, well, actually the first part on the left, is, defined as the curl of the electric field, which, as we know, is a cross product of the gradient multiplied by the electric field. Now, if you remember the electromagnetic wave, the electric field here is only defined on the y-axis, which is why we get this here. And of course, the gradient by definition is this. And then we have also to remember, the definition, well, something we've seen before regarding the cross product, the result of the cross product is equal to that. Now, if we apply that to this cross product here, what we get for this particular one here is, first coordinate of first vector multiplied by second coordinate of second vector. So that would be d over dx by ey. So that's partial derivative of ey over dx minus something which is 0. And by also seeing that this, of course, is equal to 0, then we get this final result here. Now, if we have a closer look here at the third coordinate, we get this equal to that, right? According to this equality here. Okay. Then, oh, nice animation. Thank you, PowerPoint. Okay. Now, we have to calculate, EY and BZ. Well, it's fairly easy, BZ. We have to remember that EY is equal to a sine wave whose amplitude is E naught here. So the function is equal to E naught times sine of the period of the sine wave, which is 2 pi over the wavelength here. And since we're moving on the x-axis at velocity equal to c over time, this is a formula we use. And same thing with BZ. Here in red, I have B naught here being the amplitude multiplied by the sine wave with a period of 2 pi over lambda b, and same thing, moving on the x-axis. So what do we get with that? Well, it's fairly easy. We have to derive this function here over t, and therefore what we do is we use b naught here, which is a constant. The minus sign here comes from there, and then we have to derive the sine, which is, remember, the derivative of a sine wave is a cosine, so that's cosine of this function, and then we have to derive this part relative to dt, so that's 2 pi over lambda b times minus c, okay, which is what we get here. Same thing for derivative, partial derivative of ey over dx. You got the constant here, which stays there, and then you have to derive the sine, which becomes a cosine, and then we derive relative to dx, and therefore that will be here 2 pi over lambda e. And then, of course, we realize that, oh, but by the way, these two functions, are periodic and they are equal. Therefore, their wavelength is equal. So lambda e is equal to lambda b, which we'll call lambda. And then that becomes, b naught times 2 pi c over lambda here is equal to e naught times 2 pi over lambda, okay, here. And the result is e naught equals b naught times c. So that's the first thing we needed to prove. Now the second thing that we need to prove is that c squared is equal to 1 over epsilon naught mu naught. And that's in vacuum because these are constants which are exactly for vacuum. So for that we're going to need the fourth equation of Maxwell. And since we are in vacuum, that means there's no current density because to get current density you need a current, and for a current you need a conductor, and for a conductor you need something which is not vacuum, because in vacuum there's nothing, okay? Well, at least in macroscopic world. So anyway, that means this value here is 0, and therefore this equation becomes that in vacuum. So I put that in blue because we're going to use it later. Now, if you remember that the curl is equivalent to a cross product, and therefore it's a cross product of the gradient by the electric field, which has a value only on the z-axis, and therefore we get something like that, well, actually exactly that, by using the usual, multiply coordinates product minus other multiplied coordinates, etc. You get this, and you get 0 everywhere else. So you can also write this in a different way. You can write this as being equal to that value multiplied by the unit vector here, and this unit vector by definition is 0, 1, 0. So if you replace that by the actual partial derivative over x, you get this. Again, we've done that before, so I'm not gonna redo it again, okay? And therefore, that means that according to that, we get this value equals to that value here. And again, partial derivative of e relative to t is equal to that. Okay, I'm not gonna do it again. And then of course you can simplify, the cosines go away, 2 pi over lambda go away, and you finally get minus b0, which is minus e naught over c, we've proven that before, is equal to that value here, okay, which remains, which implies that c squared is equal to 1 over epsilon naught mu naught. Voderat demonstrandum. That's Latin. Oh, I'm so good. Okay, anyway. For fun, we can also have a look at the values here of these constants. And I'll let you, find on the internet if you want to why these are the values. But anyway, these are the values, okay? For the electric permittivity here, that's 8.8 something times 10 to the power minus 12. So it's very, very small. Farad per meter. Then the magnetic permeability here is equal exactly to that value. Again, you can check on the internet why, if you're interested. It serves no purpose here, okay? But it's just for fun. Is equal to 1.25 10 to the power minus 6 Henry per meter. And then if you calculate, you take those values and take the inverse of that, you get something like that, okay? Then you take the square root of that and you finally get the approximate value here for C, which, as we'll see soon, is actually the exact value. Oh, that is magic. Anyway, the 1 farad is, equivalent to 1 ampere times second per volt, and 1 Henry is equal to 1 volt times second per ampere. So if you do, the multiplication, you get, square seconds over square meters. And if you take the square root of the inverse of that, you get finally meter per second, which is good because that's a speed unit. And so C is the speed of the, light. So if we take this number, meter per second, well, we get the official value of C, because actually it's not even close. It's strictly, exactly equal to that value since the end of the 20th century, where when the some great thinkers said, well, let's define meter that way, as opposed to some more complicated way involved with molecules and atoms and whatever, I don't remember, and it's really not interesting. But anyway, now the true value is this. And in vacuum, of course, because, yeah, that's for vacuum. Okay, well, what next? Yeah, this is a good one. This English guy who works on a theorem about conservation of energy in an electromagnetic field, and he needs to define a vector. And it's called pointing vector because the guy's name is pointing. Can you believe? I know it's not funny, I know, but you have to do it every time you talk about the pointing vector. So I'm sorry. So anyway, so this guy works on this theorem, and he defines a vector called pi. This is uppercase pi, which represents the energy flux of the electromagnetic wave. So you have remember, you have the magnetic field, and you have the electric field, and then you have the propagation of the electromagnetic wave, and pi basically represent that. And so what pointing shows is that pi is actually cross product, because obviously it's orthogonal to both the electric field and the magnetic field. Except he uses H, which is similar to what we've called so far the magnetic field B. Actually, H is called the magnetic field strength, and B is the magnetic flux density. Basically, H is independent of the medium, and B depends on the medium, which is why all you have to know is that in vacuum, H is just proportional to B, like that. So it's you can say it's very similar. In any case, well, H is in ampere per meter, and B unit are Teslas. Anyway, so once you know that, what you can do is derive from the fact that pi is a cross product of E and H, and by definition that means that the module of pi is equal to module of E multiplied by module of H multiplied by the sine of the the angle between the two vectors, which, as you remember, in the example we take here, is 90 degrees, which is pi over 2. And since sine of pi over 2 is equal to 1, that means that the module here is equal to the product of the modules there. Okay, so from that we replace E by its value that we've already seen here. And H, well, H is equal to 1 over mu naught B, which is there because B, as you remember, for the module would be equal to E naught over C, and that becomes, this part here. And from that, well, we can say, we have E naught here, so that's E naught squared, then we have twice the sine here, so the sine square multiplied by, well, what remains here, which is 1 over C multiplied by mu naught. And that will be, by definition, the instantaneous intensity. Instantaneous because, it depends on time. But since it's a periodic function, it's not very useful to get the instantaneous intensity. What you really want is the average value, over a period of time, because it's varying all the time. And if you remember, we've seen before that the average value of sine square is equal to 1/2. And of course, the average value of a constant is a constant itself. So the average intensity of pi will be equal to 1/2 times 1 over C times mu naught times E naught square, right? Yeah, right. So that's what you get here. Remembering that what we've just seen before, which is C squared is equal to 1 over nu naught times epsilon naught. So you replace that with this, and you finally get that. Now, if you remember that intensity can also be defined as energy per unit volume times velocity, and this is velocity here. So that means if you remove the c, if you divide by c, you get the energy per unit volume, which is by definition, the energy density. And that means that the energy density is proportional to E naught square. And energy density being the energy per unit volume means, number of photons per volume. Okay, so we'll have to remember that, and we'll use that in the final part of our derivation. Okay, so now it's time to look at what Malus did, So what he actually did is he took, some kind of lens and had some, light ray going through it, and he realized that depending on how the lens was oriented, the intensity of the light after the lens was changing. It was either just leaving the light unchanged, or if it went to 90 degrees angle, nothing was going after the lens. Am I blind or what? And then he wanted to determine how the intensity was varying after the lens depending on the orientation. Okay, so here is a representation. So you have the light coming there through the lens here, and depending on the angle here, the intensity of the ray here will change. Okay, so let's see how. Okay, so the first thing we need to do is to consider here the electric field, because actually this is called polarization. Okay, and polarization is just the orientation of the electric field. So let's take the electric field vector here and replace it with the sum of these two vectors here, and this vector will be aligned with the filter orientation, which means when you're that way, you get full intensity of light after the filter. Now, by definition of the cosine of this angle here will be equal to that side over that side. Therefore, cosine of theta angle here is equal to Ex over E. Okay. Now, if we look at the intensity, after the lens, it will be proportional to Ex squared. That's what we've just seen before. Therefore, it will be equal to or proportional to E squared times cosine square theta. Okay, because of this. But before the lens, it was equal to, it was proportional to E squared. Therefore, if you look at those two formulas here, that means that the intensity after the filter is equal to the intensity before the filter times cosine square of the angle. Hey, that's the Malus law. Wow. Isn't that interesting? Not yet, but soon you'll see it's very interesting. Because now we are going to give an interpretation of that. Okay, so basically what Malus said is well, the light intensity will be decreased by a factor of cosine square theta. And remember that cosine square theta, of course, will vary between 0 and 1. So it will always be 0 to the same value as it was before. And that's based on the angle between the light polarization and the filter polarization. Okay? Yeah, okay. Now, when finally we realized, early in the 20th century that light was actually an electromagnetic wave, and it was made of photons, according to a guy called Albert Einstein, we said, okay, well, let's think of the application of this at photon level. Okay. Well, first, the color of light didn't change before and after the filter. Red before, red after. Blue before, blue after. Got it? Yeah. In fact, since the color is equivalent to the frequency of light, that meant that light intensity was not due to the energy change. Why? Because Mr. Einstein told us that the energy is proportional to the frequency. Therefore, since the intensity of light was weaker after the filter, it had to be another reason, and another reason was just the number of photons, going through the filter. And therefore, the statistical probability that a photon pass the polarizing filter is equal to cos square theta, because of Malus law. All right, so that's something that we need to keep in mind. And finally, that will help us to get to the Bell's Inequation. Aren't you excited? Oh, I am. I am so excited. It's gonna be fun. See you next video.